Hi, this is Theoretical Computer Science. We're doing section 1.3 of Sipser's book. We're talking about regular expressions, and my name is Noson Yanofsky. Okay, so we've been talking about regular expressions the whole time, but we didn't really call it that, and we just put down these things. Every time we did a language, we wrote down a little formula for what it's all about. Okay, we've seen this formula before. We've seen these regular expressions before, but I wanted to give you an intuition of what they are. Okay, and we've seen something like that in the beginning of your computer science degree when we talked about numeric expressions, not regular expressions, numeric expressions. They're ways of talking about formulas of numbers. Okay, and so you could say as follows, and I'm not being exact here because we're not interested in numeric expressions, we're just getting a feel for it. You could say as follows: what's a numeric expression? Well, a number, a variable, okay, and if n1 is a numeric expression and n2 is a numeric expression, then n1 plus n2 is a numeric expression. Okay? You might want to put parentheses there. Again, if n1 is a numeric expression, that means it's made out of numbers or variables or something like that, and n2 is a numeric expression, then n1 times n2 is a numeric expression. Okay? And then if n1 is a numeric expression and n2 is a numeric expression, you can subtract, and n1 you can divide. Okay, so these are the operations one can do to numeric expressions to make other numeric expressions. Okay, that's great. Okay, and then if I write down a numeric expression like 3 times z plus 7 divided by y minus, let's use a different number because we already here, 5. So basically 3 is a number, z is a variable, 7 is a number. Since z is a number and since z is a numeric expression and 7 is a numeric expression, we can add them. This becomes a numeric expression. This becomes a numeric expression. Y is a variable. 5 is a number. Minus is an operation, so this becomes a numeric expression, etc., etc. Okay? But we're not interested in numbers, and so we're interested in what a regular expression is. Okay? And let me tell you what it is. Okay? There's 6 rules. Okay, if A is a member of the alphabet, then the A by itself is a numeric expression. Okay, great. What else? The empty word, which is not in the alphabet, is a numeric expression. Next, the empty language, this symbol is a numeric expression. What we're going to see, okay, fine. Okay. 4, if R1 is a regular expression and R2 is a regular expression, then the union of them is a regular expression. So that's an operation. And again, we can put the parentheses. I want to leave the parentheses off. Okay. 5, if R1 is a regular expression and R2 is a regular expression, then we can do that operation and get another regular expression. And finally, if R1 is a regular expression, then R1 star is a regular expression. Okay, so this is the way we build up regular expressions. So, for example, B composed A. Okay, B is a regular expression, composed is a regular expression. B is a regular expression, A is a regular expression. We can compose them, we get a regular expression. Star of them, that's great. Okay, okay, and then union A composed B composed C star is a regular expression. Okay, something like that. Okay. we'll assume parentheses here, but that's fine, it doesn't matter. Okay, now just for the hell of it, just to make things a lot easier, I'm going to have two things. First of all, we're never going to write these little zeros. Okay, they're a pain in the neck, and they remind me too much of 0. Okay, so we leave them out. Okay, and the next thing is, although only these three operations are ways of making numeric expressions, we have the following additional one that we do also. Namely, if R1 is a numerical expression, then we do R1 plus. What does R1 plus mean? It's just a shorthand way of writing R1 composed R star. R1 star. Okay? Well, another way of writing it is R1 star composed R1. In other words, it's 1 or more. Whereas R star corresponds to 0 or more, R1 plus is 1 or more. I don't care if you put the 1 on this side or the 1 on this side. Okay, so we'll be using plus also. The main point is as follows, and this is the main point of this section, is that for every regular expression corresponds to a language. Every regular expression corresponds to a regular language. Okay? And we can almost see it. Okay? What language does this correspond to? Language. Well, it corresponds to the stupid language that has one word, and that one word has one letter, A. That's it. Okay? What does this correspond to? It corresponds to the language that has one word, and that word is the empty word. What does this correspond to? Well, that corresponds to the language that has no words whatsoever. What does this correspond to? Well, if a regular expression corresponds to a language, and this regular expression corresponds to a language, then this regular expression corresponds to the union of them. And if this regular expression corresponds to a language, and this regular expression corresponds to a language, then this is going to correspond to the concatenation of those languages. And if this regular expression corresponds to a language, then this, with the whole thing with the star, is going to correspond to the star of the language. Okay? Okay? And then something like this is going to correspond to a bunch of BAs, words that consist of a bunch of BAs, could be 0, or words that consist of, a word, and this is a word, this is words that consist of A followed by B followed by a bunch of C's. Okay? So a bunch of BAs, BA, could be 0, or let's leave out the parentheses here. Let's redraw this. This is A, B, C star. Okay, BAs, or words that begin in A, B, and then end in C. Okay, great. Okay, great. Now we're going to do a few examples of, I'm going to give you a language and I'm going to ask you to write the regular expression that corresponds to it. Okay, we're going to do easier examples first. We're going to do before that, let's do let's just mess around. Okay, A union B star is every word possible. Let's take it. The alphabet is A comma B. Then A union B star means give me an A or a B, give me an A or a B, give me an A or a B, etc., etc. As opposed to that, A star B star, that corresponds to words that are a bunch of A's followed by a bunch of B's. Okay. The language that corresponds to this, and there's a language that corresponds to this, and this language is a subset of this. Okay. I'm now confusing the regular expression and the language. Okay. Now, how does this compare to this? That's a concatenation there. How about this? A star union B star. Okay. This is also a subset of this, but what does this correspond to? This corresponds to words that are either a bunch of A's or words that are a bunch of B's. Okay. Now, is this a subset of this, or is this a subset of this? Okay. It turns out this is the subset of this. Because look, what's these words? They're a bunch of A's. Well, if I make B 0, that's a bunch of A's. Or a bunch of B's, well, cover over the A's, that's a bunch of A's. Okay, so you have a lot of these different things. How do we write an even number of A's? It's an even number of A's. By the way, that's a subset of this. It's also a subset of this. Okay. How do you write so this is an even number of A's. How do you write an odd number of A's? That takes care of that. What's an odd number? It's an even number plus one more. Okay. Let's do some more. Let's do some more. We're going to do some homeworks problems. We do some homework problems. I'm sorry, some exercise from the back of the book. 1.18. I think this is L. Okay, and it goes as follows. W contains an even number of zeros or exactly two ones. W contains, okay, so the alphabet is 0, 1, contains an even number of zeros or contains exactly two ones. Okay. Main word here is the word or. Okay. And when you want to do or, you know that that's going to be this. Okay, so now we could split the problem in half. How about contains an even number of zeros? This is very simple. Okay, I don't care how many ones there are, but it contains an even number of zeros. So what you do is, we saw an even number of zeros, that's this, with a star in it, right? That's an even number of zeros. But now, I also want as many ones as you want, so put in ones. Put in ones here, put in ones here, put in ones here. Great. Contains exactly two ones. How do you do that? Well, 1, 1. But now I don't care how many zeros there are, so I can put that, or that, or that. Okay? But it's not more than two zeros, it's not even number of zeros, so I don't put a star here. Okay? That takes care of that. There are lots more examples on page 65 of the book. Let's do some more. W contains at least two zeros and at most one one. Contains at least two zeros and at most one one. Okay, W contains at least two zeros and at most one one. Okay, so the way to do this is the word and. Now that's a little bit harder than or, okay, because we have an operation for or, but we don't really have an operation for and. Okay, but what I can do is I can look at this part. What does this mean? At most one one. Okay, that means it has 0 ones or 1 1. Okay, so let's write that out. 0 1 or, you're going to see this or, that's going to correspond to that. To the union, or 1 1. Okay. And at most 1 1. Okay, so how do you write this? I want something 0 ones and contains at least 2 zeros. Okay, so the way to do that is 0, 0, 0 star. Contains 2 zeros, it could have more. Does not have any ones, or at most 1 1. Okay, now this is a little bit of a pain in the neck. Again, contains at least 2 zeros, so it's going to be 0, 0, 0 star. Okay, but it contains 1 1. Where does the 1 go? Well, there's a lot of possibilities, so let's put all the possibilities. The word could begin with a 1, or the word could have a 1 after one of them, or after 2 of them, or have 2 zeros, have many more, have a 1, and have more zeros. Okay, and I think that's it. Okay, what about ending off in a 0? Well, words that end, ending off in a 1, words that end in a 1 will be described by this too. Okay? Okay. Anyways, by the way, this can be shortened to O plus, this can be shortened to O plus, this can be shortened to O plus. Okay. Anyways, the union of this gives you this language. Okay? Okay. Just for completeness, we're going to do the rest of 1.18. Okay, in fact, we did some of them already, but we're going to do the rest of 1.18, and for homework you're going to do the earlier parts. Okay, so let's just do this. 1.18k is the language, the empty word and 0, and that's simply the empty word or 0. Okay, the empty language, this is M. The empty language, that means the language that has no words, and I showed you what that is, that's that. Okay, 1.18n is all strings except the empty string. All strings except the empty string. Okay, well, let's just do it. I mean, all strings is that. Okay, but we don't want that because this could be 0 and that would be the empty string. Okay, so what we want is that. That's it. Okay, let's just write it an equivalent way. That's that. Okay, let's erase this. Okay, 2 more problems, not from the book, from a different book. Again, with these things, you have to see a lot of examples, and then it comes easy. Okay. Okay, I just want to show you how this one works, because there's 2 ways of doing it. It's not hard. Okay. W, such that W contains no more than 1B. Okay, we saw something like this. Okay, just use different language, but we saw something like this. Let me rewrite it. Let me restate it in English. This is an equivalence of English. W contains at most 1B. So we know how to do at most 1B, but the point is it's 0 B's or 1B. Okay, and the usual write is, And one way of doing it is saying, okay, 0 b's. That means a star, or a star is 0 b's, or there's 1 b. Well, the 1 b could be a squared, a star, b, a star. That's it. Have a bunch of a's before, have a bunch of a's afterwards, but have 1 b. Okay, that's one way of doing it. I just want to show you another way of doing it, which I like even more. Okay, this is the same. You're going to get the same language. It's just a different way of saying it. It says, look, start with a bunch of a's. Compose with either 1 b or no b's. Finish with a bunch of a's. Okay. Okay. Great. Another problem from another book. W such that no two, let's leave out 2, consecutive letters are the same. No consecutive letters are the same. Okay? What that means is as follows. If you start with an A, the next letter has to be a B. The next letter has to be an A, the next letter has to be a B, the next letter has to be an A, etc., etc. But you could start with a B, the next letter has to be an A, the next letter has to be a B, okay? Or you can have B, A, B, A. Okay? How do you do that? Okay. Now obviously there's a lot of pairing here. So depends how you see it. You can say, oh, there's a lot of A, B's here. But 1 second. I don't necessarily have to start with an A. I could start with a B. Okay, so you can do the following. B, or I could start with the A. That way we write this. Great. So it's a bunch of A, B's, but I could start with a B. Okay, also, this one definitely ends with a B. Okay, I could end with an A, or I can end with a B. So that's that. Okay, you can also write this as that. Okay, a bunch of BAs. And you can write it as here's just another way of writing it. A bunch of ABs followed by an A or epsilon, union a bunch of BAs followed by a B or an epsilon. Okay. That takes care of that. Okay, so we saw like 10 different examples. Homework has some more examples, and definitely a possible test question. Definitely. Okay, great. Next, theorem. A language is regular if and only if some regular expression describes it. Okay. Now, I'm going to prove, well, let's first see what it says. It says, a language is regular. What does it mean for a language to be regular? It means a finite automaton recognizes it. Okay? And what type of finite automaton? Well, we had lots of different types. We had deterministic, non-deterministic with epsilon moves. We don't care. Okay? But a language is regular if a finite automaton recognizes it. Okay? But now we're saying, oh, here's another thing. Regular expression describes it. So that's another way of describing a finite automaton, a regular language, using regular expressions. Okay? Now, it goes both ways. You give me a finite automaton, I'll give you a regular expression. You give me a regular expression, I'll give you a finite automaton. Okay? Now, this way is perfectly legitimate, and the book does it, but we're going to skip it. Not because it's too hard, not because we don't want to deal with it, just we want to cover a lot more material. So it's 5 pages in the book, and the way it works is as follows, and you can read it on your own. Basically, you take a finite automaton and you crunch it together till you have 2 states. You bring things together until you have 2 states, and those 2 states basically have, how do you get from here to there? This is an accepting state. Well, you have that regular expression on top of it. Okay? Okay. Okay. We are going to do it this way, and I'll show you how. Okay, just give me a second. Okay, the other way, if you give me a regular expression, find me a finite automaton that recognizes the same language as that. Well, we did that already. Okay, let's just go through some of it. Okay. Here's a finite automaton that just accepts the word A. That's it. Here's a finite automaton that just accepts the empty word. Here's a finite automaton that accepts the empty language. And we did this. This is the center part of section 1.2, where we showed how if you give me a regular language and you give me a regular language, the union of them is a regular language. If you give me a regular language and you give me another regular language, the concatenation is a regular language. If you give me a regular language, the star of it is a regular language. We did this. Okay, that's the point of this. That's the point of what we did. So, point. You give me a regular expression, I can find you a finite automaton that's going to accept that same thing. Let me do a real live example of this. Again, the book does a different example, but it's fine. Okay, a real live example is as follows. You ready? Okay, that's simple regular expression, and it's not interesting. It's not an interesting. It's not an interesting language. It's either a 0 followed by a bunch of 1s or 1 by itself. Okay? But the reason why I chose this simple language is because it has all 3 operations. Okay? And when you have all 3 I want to show you how you do this. So the way you do this, I want to find a finite automaton that describes this language. I'm sorry, I want to find a finite automaton that recognizes this language. So let's do it, okay? The way you do this is, let's put in parentheses so we can see things, okay? And what's in parentheses? Well, let's first do the 0, then do the 1, okay? You break apart and go into it and find the subparts, and then you build up using those operations, okay? So let's do this. This is the finite automaton that finds the letter 0. This is the finite automaton that accepts the letter 1. Great, now we have that. Now let's do 1 star. This is the finite automaton that does 1 star. How do you do 1 star? We did this. You add in a new starting state, which is an accepting state. Then you bring it together with this. Okay, that's the new thing. And you have return to the beginning thing. This is an epsilon move. Okay, that's 1 star. Okay, so we did 1 star. We did this, and with this we did this. Great. Now, what I'm going to do is finish off what's inside the parentheses. I'm going to concatenate this machine and this machine. Okay, because that's what it's called for. So let's do it. You ready? Concatenate. So now we're going to do 0, 1 star. So how do you do it? You take this machine. Okay, and then you concatenate. You have an epsilon move, okay, to this machine. Okay, but hold on. When you concatenate this machine to this machine, you better make sure that this is not an accepting state. So we have to undo this as an accepting state. Okay, great. Now, that's perfect. But now I want to do union with 1. Well, 1 we already did so let's do the final thing. How do you do a union? You start with a new starting state. Okay, and you go to 2 other starting states. We're going to do it with this. So this becomes that. That's one of them. Okay, and then this becomes what? Zero, epsilon, epsilon, and we go back. Great. And that's it. Okay, that's it. We're finished. Okay. Now, obviously, I can make a long, complicated. I will on a test make a long, complicated one and make you work it out all the details. Okay. But this has all the ideas because this has all the operations. This has all the ideas you need. Now, by the way, this is a little bit long. There's no reason to have 2 of these epsilons. Okay, one after the other. That's not a good idea. I'm sorry, I think this should be in an accepting state. Why isn't this in an accepting state? Hold on, don't move. No, it is. Okay, fine. Great. Okay, so we can actually shrink this. And let me show you how you shrink this. This can shrink to one thing, and so you get something like this. I'm going to shrink it 2 times. Okay? One is just leave this as it is. I'm sorry, maybe I should have put this on the bottom. That's fine. Okay, because this came first, but that's fine. And the other is, let's shrink this as a 0. Okay? Followed by, you can crush these and just say, look, 1, but you know what? When I do a 1, I want to stay where I am. So I'm going to make this an accepting state and put a 1 over there. Okay? So there are many different finite automatons that recognize the same language, which is perfectly legitimate. Okay? Let's just shrink this another way, even further. Look, you have a 1. It's an accepting language. Or you have a 0 and then a bunch of 1s. So you can crunch these 2 into nothing and then you get that. Okay? And that's pretty good. That's only 3 states. Okay, that takes care of that. Okay, good. Before we close, let's ask some questions. Okay? What's a finite automaton for this language. Okay. Well, you can do it the same way, and basically it turns out to be like this. It's a bunch of A's followed by a bunch of B's. Okay, this doesn't have to have that on, but that's fine. Okay, great. Next, what about a finite automaton that does this, where the number of A's and the number of B's are the same? Stop the recording, sit down with a pen and paper, and try to work it out. Okay? I'm waiting. Stop the recording. Try it. Try it for 10 minutes. Okay. I assume you tried it? Okay. So let me tell you one possibility. You could say, oh look, I know how to do AB. I know how to do AABB. I know how to do AAABBB. So just keep on doing it. So how about this? Start off in a state like that, and then try something like this, A, B, accepting state. Then try, I'm going to just do this a little bit quicker, A, B, B, accepting state. And then try A, B, 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 accepting state. Dot, dot, dot. The problem with that is that is not a finite machine. Dot, dot, dot means as big as you can get. Okay? That's not good. Okay? So that's not good. Because a finite automaton has a finite number of things. Okay? So that's one attempt, and you're going to fail at that attempt. How about another attempt? Is there another clever way of getting this machine? The answer is no, there isn't. The answer is no, there isn't. Okay? And not that I can't do it, or Professor Cox can't do it. Okay? It can't be done. If Albert Einstein came in, he couldn't do it either. Okay? It's an impossibility. You cannot make a finite automaton that does this language. In fact, that's the purpose of this. We're going to go up this chart. We see that there are certain things that a computer cannot do, a finite automaton cannot do, so we have to go to more sophisticated and more complicated machines to determine such a language, to recognize such a language. Okay, so this is what I'm trying to show you is regular languages is just the beginning of the story. We're going to go higher and higher to do this. Now, how do I know that I can't do a finite automaton? Yes, the thing I showed just doesn't work, but how do I know it? Okay, and so let me just tell you, in section 1.4, they show you how to prove that a certain language is not regular. We're skipping that section, not because it's too hard, not because it's uninteresting. It's actually very interesting. It's the first example we see of a computer that cannot do something. So it's a very interesting thing. Just in terms of time consideration, we don't have time to go through that very carefully, and so we're going to spend some. So we're going to skip it. Okay? But I just want to show you what's in that section. There's a way of showing that certain languages are not finite. Are not recognized by finite automatons. Okay. By the way, it's called pumping lemmas. Okay, and you have to understand what it is. But these are ways of proving that certain languages are not regular. Okay, and that is the end. Okay, that is the end of section 1.3. Okay, great.